Welcome to the joint session, Algebra and Lie Theory and Generalization. I am Toshiyuki Kobayashi from the Tokyo University. The next speaker is Michael Larsen from the Indiana University, United States. Michael Larsen obtained his PhD from Princeton University in 1988 under the supervision of Faltings. He joined the Indiana University faculty in 2001. Michael Larsen is one of the universalist mathematicians who is working in so many areas of mathematics. And as such, his work has built bridges between different topics and very often in a quite unexpected way. The title of his ICM talk is Character Estimates for Finite Simple Groups and Applications. So please.
So thank you for coming to my talk. My topic today is character estimates for finite simple groups and applications. And I'm going to start with some applications because without them, I think that the character estimates would be a bit dry. Okay, so let me begin with actually a famous problem of Diaconis-Shahshahani. So they consider the class of transpositions in the symmetric group, and they do a random walk on T, and they ask what is the mixing time for this random walk. Now, okay, they actually have to do the thing in a slightly different way because otherwise in an even number of terms you'd only get an even permutation, and in an odd number of terms you'd only get an odd permutation. So they actually throw in maybe a 1 in n probability of the identity. So this is just a small technical point. But in any case, they look at this random walk and they ask how many steps does it take. So by mixing, they mean that the total variation distance, which is basically the L1 distance, between the distribution of the random walk and the uniform distribution on the symmetric group is less than some small constant that you use as a cutoff. So what is that time? And what they found was that the amount of time that it takes is 1/2 times n log n plus an error of order n, which also has built into it the question of how big this small constant is. Okay, so that's the amount of time it takes for a random walk of this kind to equidistribute over the symmetric group. And one thing which is kind of striking about this, if you think about it for a minute, is that the amount of time that it takes grows more rapidly than the covering number of this set of transpositions. And by that I mean the number of transpositions necessary to write an arbitrary element of the symmetric group as a product. So every element of Sn is a product of at most n-1 transpositions, whereas it takes something like 1/2 n log n random transpositions before you equidistribute. So there's a kind of an intermediate behavior where you have more than n steps, but less than n log n over 2, where every element in the symmetric group gets hit, but some get hit a lot more often than others. So that was what they discovered, and this has been generalized by other people. In particular, I mentioned a result of Roichman. And what he did is he considered, instead of transposition, he considered he looked at conjugacy classes where the number of fixed points, which we'll call n-k of elements in the conjugacy class, is not too small compared to n. So the original problem involved k equals 2, so you have n-2 fixed points. That's a transposition. So Roichman considered k, which was, let's say, well, such that n-k is bigger than a fixed multiple of n. And what he discovered is that the mixing time grows like 1 over k times n log n in this generality. So that's the the case of symmetric groups, it also, I mean, one could also look at the same problem for alternating groups, obviously not with transpositions, but you could use 3 cycles or some other conjugacy class with large number of fixed points, and you would get the same behavior. So the alternating group somehow is understood, and so the question therefore is what happens with the other big class of finite simple groups, namely groups of Lie type. So there's a conjecture which is due, I guess, in independent papers to Globotsky and Shalev, which predicts that if G is a finite simple group of Lie type and C is a conjugacy class, then the mixing time for a random walk with this generating set C, so each element in C is equally likely as a step, should grow as the order of log to the base C of G. And I should say that this is kind of the smallest amount of time it could possibly take. Otherwise, most elements of G won't be visited at all. I mean, it's just impossible. If you choose less than log C of G, most elements just won't be visited at all. So the conjecture is a theorem now. It follows from character estimates that I proved with Guralnik and Dieppe, and which I'll talk about at the end of the talk. But I do want to mention, before doing that, that before looking at mixing time, people did look at the question of covering number. And what Liebig and Shalev proved in 2001 was that the covering number is also kind of, at least in terms of order of growth, as small as possible, log to the base C of G. So in this case, there isn't really a divergence in growth rates of covering number and mixing time. This is one example where the 2 big classes of finite simple groups behave rather differently. So that's this mixing time business. And another problem which kind of motivated our study of these character estimates was Waring's problem for finite simple groups. So of course the classical Waring problem is about integers, and you want to write every positive integer as a sum of nth powers for some fixed positive integer n. And the question is, how many nth powers does it take? So for example, it's a famous theorem that it takes 4 squares, and so on. But it turns out that in the finite simple group setting, it actually suffices to use 2 nth powers. That is to say, if you fix n, the question was, does every sufficiently large finite simple group have the property that each of its elements can be written as a product of 2 nth powers? And it turns out that the answer to that is yes. And just as with the covering numbers versus mixing time problems, there's a probabilistic version of the same problem. You could ask, suppose we choose 2 random elements and multiply their nth powers together, and ask whether the resulting product approaches uniformity in this total variation sense as the order of the group goes to infinity. And if you think about it for a minute, you'll realize that neither one of these questions implies the other, but in fact, both of the questions have an affirmative answer. Now, there is a third question we could ask that I didn't put on this slide. I think the question would be the following, which is, instead of looking for this convergence in a kind of L1 sense for a random product of 2 nth powers, you could look for a convergence in an L infinity case, L infinity sense, where each element of the group becomes equally likely up to a small quantity epsilon. And you could ask how long that takes. And here it turns out that 2 nth products is not enough. It requires a number of nth products which depends on n, sort of more like the classical Waring problem. But again, this will happen as G goes to infinity if you have enough nth products, and that enough does not depend on what G is, it just depends on what n is. I should also maybe say that if we think about the expression x to the n, y to the n, what's sort of special about it, and what the proofs use, is the fact that it's a juxtaposition of two non-trivial words in disjoint variables. So you have a bunch of x's and a bunch of y's, and you don't end up like no x's appear in the y section and no y's appear in the x section. So more generally, one can prove a Waring problem type result for such products of two words in disjoint variables. Okay, moving on to Ora's conjecture. This is a problem that I was not involved in, but I think it's a beautiful result. And the conjecture, the 1951 conjecture of Ora, was that every element in any finite simple group is a commutator. Not that it's a product of commutators, which is more or less obvious, but that it can be written as a single commutator. And this was settled finally by Liebig, O'Brien, Shalev, and Dieppe in 2010. And it used a number of methods, not just character estimates, but character estimates were an important ingredient. Even harder than Ora's conjecture, or at least so it seems, is Thompson's conjecture, which asserts that for every finite simple group G, there is a conjugacy class C whose square covers the whole group. If instead of looking at C times C, we looked at C times C inverse, this would be a variant of Thompson's conjecture, and that variant would actually imply, in a very straightforward way, Ora's conjecture. But in fact, as I say, I mean, Thompson's conjecture seems to be the harder problem. It's still open. What we do know, thanks to work of Ehlers and Gordeev, and other people as well, but especially this paper, we know that Thompson's conjecture is true, except possibly for certain infinite families of groups, and these are families of groups of Lie type over particular small finite fields, nothing with more than one digit. Now, it turns out that several of the families that remained after the work of Ehlers and Gordeev can be handled using the character estimates that I'll talk about later. Unfortunately, even if we succeeded to the full extent of what we hoped to do, which would mean that we would handle all the remaining infinite families, the methods are asymptotic, and so there would still be a finite list of cases, which I don't think could be handled by these character methods, which have a kind of asymptotic character, as I think will become apparent. Okay, changing gears a little bit, let's look at Fuchsian groups and their representation spaces. So let's start with a co-compact Fuchsian group. So this is a subgroup of PSL2R with a discrete subgroup with a compact quotient. If you don't think about Fuchsian groups normally and want sort of a concrete class of examples to think about the fundamental groups of genus G, compact-oriented surfaces of genus G, where G is greater than or equal to 2. And we also let G be a complex semi-simple Lie group. And what we're interested here is in the homomorphisms from gamma to G. Because gamma is a finitely generated group, we can actually, and because G can be thought of as an algebraic variety, as well as being thought of as a group, G is a complex algebraic variety, we can think of the homomorphisms from gamma to G as being a variety in its own right. And but we can look at the complex points of this variety, so we can just think of this Hom just in terms of thinking of G as a complex Lie group, so we get a complex manifold. Well, at least we get a, I shouldn't say complex manifold, we get a, well, it could be singular, but it's a complex space. And we'd like to understand its topology as much as we can. At the minimum, we'd like to understand its dimension. I should say that what we would probably really most like to understand is the quotient of Hom from gamma to G by the diagonal action of G. That's like conjugacy classes of homomorphisms. That's sort of the really important object, and that we can think of as G bundles on some kind of a space associated to flat G bundles on some kind of a space associated to gamma. But as a starting point, we'd like to understand the homomorphisms. And for example, it would be nice to know whether this dimension formula always holds, at least if G is, let's say, a complex simple Lie group. And we know that in some cases, for example, for genus greater than or equal to 2, that it does. This seems like the kind of thing that ought to be approachable in general using character bounds. Exactly what they can do for us is not so clear for this problem. In fact, this problem seems a little bit different from the others in that it's not about finite groups per se. It's about Lie groups. So there's some algebraic geometry step that we would need to do to reduce from these complex semi-simple Lie groups to families of finite groups. So for example, if G is SLN of C, we would presumably want to look at SLN of FQ for large finite fields FQ. So there's various things that we would need to do, but ultimately it should reduce to some kinds of questions about characters of finite simple groups, or maybe central extensions of finite simple groups. Now, how do characters enter the picture? So the problems, as I stated them, are mostly, maybe the last one is a little different, but they're mostly about conjugacy classes. And what is the relationship, from our point of view, between these conjugacy classes and characters? Well, I mean, of course, there is a relationship. The form in which this relationship is perhaps most conveniently stated is this theorem of Frobenius. And this asserts the following. So we start off with an arbitrary finite group G, and we have conjugacy classes C1 through Cn. And what we're interested in is counting the number of n tuples of elements of G. The first element, x1, is in C1, x2 is in C2, and so on up to xn and Cn. So one element in each conjugacy class, which have the property that if you multiply them together in the specified order, you get the identity. You want to count the number of these n tuples. Now, if we were just kind of doing this in a heuristic way, we might reason as follows. We might say, well, the number of ways of choosing an n tuple if we don't impose this condition would be the numerator of this fraction, number of elements in C1 through across dot 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 cross Cn. And if you choose any such n tuple and ask, well, what is the probability that the product is equal to 1? You might guess that there's no reason it should be more likely to be one element of G than another, so that would give you a factor of G in the denominator, and so that would be sort of perhaps your naive estimate of how many points there are in this set. In fact, this turns out to be exactly right, except that there's a correction factor, and this factor is a sum over the irreducible characters of G of this fraction. And maybe the most important thing to understand about this fraction, well, first of all, the numerator has character values, and the denominator has the degree of the character. But the kind of key thing which makes this formula a little hard to work with is that the number of factors in the numerator is n, whereas the number of factors in the denominator is just n minus 2. So even if you understood perfectly well well, I mean, if you look at the values of a character of a finite group, the absolute value of a character of a finite group at any element of the group is always less than or equal to chi of 1, because you're just adding together a bunch of roots of unity. So that the absolute value of a sum of roots of unity is less than or equal to the number of roots of unity. So that each term in the numerator is less than or equal to chi of 1, yes, but there are more of them, and of course there's also a sum over irreducible characters of G. And so there's some issue that needs to be overcome if we want to say that in this sum, the term chi equals 1, the trivial character, dominates all other terms combined. If that were true, if the main term in the sum is 1 and everything else combined is sort of trivial, then the sort of naive estimate, the probabilistic estimate, would be right. up to small error term. So that's what we would like to do. We'd like to know that maybe we have to make n big enough or something like that, but we'd like to make these fractions small. That's I think the main reason why in these applications we care about upper bounds for characters. Okay, now as I sort of indicated, we're interested in character ratios. We want to understand the relative size of chi of g and chi of 1, and we know in advance that this is less than or equal to 1. And since we're dealing with simple groups, the center just consists of the identity, and so if chi is a non-trivial irreducible character, then this will be strictly less than 1, but how much less? Now what we would most like in terms of the Frobenius formula would be an exponential character bound of this kind. Chi of g is less than or equal to some power of chi of 1, the idea being that we could then sort of add up the exponents. If you look at the numerator, right, we have the product of character values in the numerator. So if we had bounds like this, you could add up the exponents, and hopefully the chi of 1, power of chi of 1 in the denominator would be enough that we could control the whole sum. So that's kind of what we're hoping to do. Now, why do I say alpha of g? Why the dependence on g? It would certainly be more convenient if it didn't depend on g, but that turns out to be really too much to hope for. So let me say a word about that and say in particular something about the centralizer bound. So if we start with an irreducible character, and this is true for any finite group, and we take the sum over all group elements of the absolute value squared, that's going to be equal to g by the orthonormality of irreducible characters, right? So that's tells you something sort of interesting, which is that the average value, or at least the average square value in absolute value of chi of g is just 1. It's most of the time it's really small. But what it tells you absolutely, rather than just sort of on average, is that if we choose any element little g and we look at the conjugacy class and we multiply by the absolute value of chi squared on that conjugacy class, that's just, since all the terms in this sum are greater than or equal to 0, this is just a subsum of this, and so it'll be less than or equal to g. And that gives us the centralizer bound, which says that you pull this conjugacy class size over to the other side, and you take the square root, and you get the centralizer bound. Now, when we have character bounds, we expect to do much better when the conjugacy class is big, right? When the centralizer is small. So we think of these cases where the centralizer is small as being regular elements. I mean, this is a kind of a loose term. And we think about the case where the centralizer is really big. Well, I mean, the worst element, of course, is the identity, but that's treated separately. So anything which is not the identity but has a very big centralizer comparable to the size of the group, we think of as being highly irregular, highly singular. And so we expect a much worse bound for these irregular elements than for regular elements. And there's a sort of an intermediate case where we might look at typical elements. And ideally, we would like our character bounds to be good all through the range. And somehow it just seems like a very difficult thing to do. And most of the character bounds you'll see, and there are quite a number of them in the literature, specialize in some class of elements. Sometimes also in some class of characters, because you see what happens is that there are usually a few non-trivial irreducible characters of low dimension. But most of the characters, typically for groups, finite simple groups, what you find is that the total number of characters is rather small compared to the order of the group. And most of the characters have degree which is almost as large as the square root of the order of the group. That's sort of typical behavior. And again, we would like our character estimates to be good throughout this range. I mean, making our bounds exponential, or finding exponential bounds, is sort of a way of accomplishing the second goal. It doesn't address the first goal unless we can say something intelligent about this alpha of g, which gives the exponent. Okay, so let's now look at this in particular cases. Let's start off with symmetric groups, and in fact with the bound that was used in this original paper of Diaconis-Shahshahani. And so let's recall that the irreducible characters of the symmetric group are given by partitions of n. there's this, of course, a Young diagram associated to the partition. And when you have a Young diagram, you can look at its transpose diagram. And that will give you a new partition and a new irreducible character of Sn, and the two are related, but you go from one to another by tensoring your character with the sign character, which is 1 on even permutations and -1 on odd permutations. And that, of course, doesn't affect absolute values. So, in fact, both the partition and its transpose, or dual, however you want to think about it, give the same absolute values of characters. And so you can use either one. So the theorem says the following. If we choose lambda 1 to be greater than or equal to lambda 1 prime, which I guess means at least as many columns as rows, which we can do without loss of generality. And we look at the character ratio of the characters associated to this partition lambda. We see that if the number of, well, if lambda 1 is less than or equal to n over 2, we have an upper bound of 1/2. And when lambda 1 is big, this corresponds typically to rather small irreducible characters. We get, well, a somewhat complicated expression, but you can look at exactly what it is when lambda 1 is equal to n minus 1, and you see that it's actually very close to being optimal. In fact, this inequality does a really good job for the most singular elements, the elements with the biggest centralizers, and those are the transpositions. And also it does a good job for the lowest degree characters. But it's, and that's what's needed for the original paper. So it's not surprising that that's what the bound does. It doesn't do well. I mean, one thing which you notice is that there's no occurrence of G on the right-hand side. So you're getting a bound for transpositions, and that's the bound you have for transpositions is the same bound that you use for all group elements. And of course, you expect to do much better for elements where the centralizer is smaller. So this is a perfect example of something which is optimized for the worst elements in your group. The opposite extreme, we could look at the Murnaghan-Nakayama rule for calculating values of characters of the symmetric group elements. And what this says, among other things, is that if we have an n cycle and an irreducible character, then, in fact, the value of the character on G is either -1 or 0 or 1. So its absolute value is less than or equal to 1, which, if you think about it, is actually an exponential bound with alpha of G equal to 0 for this particular kind of G. And that's the only case I know of where you get such a good, meaning such a low, alpha of G. If you want to extend this method beyond n cycles, well, you can look at elements which have, have 2 orbits or 3 orbits. If you fix the number of cycles, then you do get an upper bound for the character value, which doesn't depend on the character and doesn't depend on n, but of course does depend on the number of cycles and grows very rapidly in the number of cycles. It's sort of factorial growth type of thing. So this then is an example of an estimate which is pretty useless for singular elements, for elements which have many cycles, but does really an excellent job when you have just one cycle at that other extreme. Okay, now I want to come to something which is, I think, really nice, the bound of Müller-Schlage-Puchta, which is maybe our first example of an exponential bound. And so the exponent is given explicitly over here, so remember that that means that the absolute value of chi of G is less than or equal to chi of 1 to this power. And you see that the exponent does depend in a certain way on G, but it only depends through the number of fixed points of G. Now there is a relationship between how singular an element is and the number of fixed points. I mean, the really singular elements have just tons and tons of fixed points, like a transposition. And in fact, the worst element of all, from a certain point of view, is the identity. Then the number of fixed points would be n. So log of n over n is log 1, so you'd have a 0 in the denominator. So this expression over here is infinite, so its reciprocal is 0. And so you get alpha of G equals 1, which, of course, for G equal the identity is the best you could hope for. So this result is exact when G is equal to the identity. And it's very good when G has a large number of fixed points. On the other hand, if you think about what it says when G has no fixed points at all, then you have an infinite denominator. So this fraction is 0, so this whole term is 0, so this is 18 inverse. So you get alpha of G is equal to 17/18, which, okay, I mean, that's a sort of a uniform estimate among elements without fixed points. But if you think about, for example, an n cycle, where the actual value should be 0 instead of 17/18, it does a very bad job. And in fact, you can see that it does no better for n cycles than it would do for something which is a product of transpositions, like, exchanges elements in pairs without fixed points. And in fact, you should do much better for elements which have a small number of cycles than for large products of large disjoint products of transpositions. Okay, well, I mean, no single estimate covers everything, and this one is great for elements with many fixed points. Okay, let me now talk about an exponential bound which I was involved with. It's joint work with Shalev. And in order to state it, it's a little bit technical to state, but I'll just kind of quickly run through this. So you take your element and you count how many 1 cycles, how many 2 cycles, how many 3 cycles, and so on. And then you define a sequence of non-negative real numbers, E1, E2, E3, which are defined recursively by this formula. And if you think about this for a moment, if there's one integer j such that your element G consists entirely of j cycles, then what will happen is that all the e's will be 0 except for ej, which will be 1. You can check that that's really true. And so, but in any case, in general, there is some formula, and the theorem is that there's an exponential bound where the exponent is given by the summation of these ei's over I plus a little o of one term. So again, in this case where you consist just of j cycles, then we would have ej over j, so this sum would just be 1 over j. So for example, if you consist entirely of 2 cycles, you'd get chi of 1 to the power of 1/2 plus little o of 1. And that case where all the cycles of G have equal length, the bound that you get is essentially the bound that Fomin and Lulov gave in 1997. So one way of thinking about our result is it's just a way of generalizing that bound to the sort of inhomogeneous case. Okay, so much for, maybe one thing I should say, maybe I said it already, but just when you talk about symmetric groups, we could also be talking about alternating groups. I mean, yeah, I think I said this earlier. I mean, the character theory is similar enough that you get the same kinds of bounds for the two classes of groups. So let's now move on to the other family of, which is groups of Lie type, and they're near relatives because you tend to treat them together. I won't say exactly which relatives, but you may see in the course of this next few minutes examples of groups which aren't quite simple. They may have non-trivial center. Okay, so let's start with Gluck's bound, which is maybe the first really significant bound concerning this kind of group. So G is a finite simple group of Lie type, and little g is a non-trivial element, and chi is an irreducible character. And so what Gluck proved in a series of 3 papers was that there exists a constant which is strictly less than 1, but does depend on the rank of G. That's the weakness of this, which gives an exponential bound for all non-trivial elements of the group and all irreducible characters. So within fixed rank, it gives a uniform exponential bound over everything, which is certainly very nice, but it doesn't allow you to take rank going to infinity. I mean, it tells you something in that regime, but it's quite poor in large rank. Okay, so that's sort of one direction, because this covers, as I said, all non-central elements or all non-trivial elements, which means that it doesn't do a very good job for highly regular elements. Okay, so here's a result about highly regular elements. This is joint work with Garion and Lubotsky. And it's something which is not specific to groups of Lie type. It's a general statement about any finite group. But the setup is such that I don't know of interesting applications except to finite simple groups. And as I say, they're near relatives. OK, so we've got our group G, and we have an element which has the property that its centralizer is a billion. And I think of this as being kind of like a maximal torus. I mean, that's my picture of what's going on in this. And then we have subgroups, proper subgroups, A1 through AN of A, such that if A belongs to the big group A, but not to any of these proper subgroups, then the centralizer of A in G is big A. And again, if you think about this, since big A is a billion and little a belongs to it, we know in advance that the centralizer is going to be at least this big. And the point of these subgroups AI is that they capture certain kinds of, like if we think about, we want elements of a maximal torus which are semi-simple, then we need to exclude certain classes, and these classes kind of give us subgroups AI. Okay, so that's the motivation. And the statement of the estimate is that for every irreducible character of G, the absolute value of chi at A is less than or equal to, well, this constant to the power of n is the number of these subgroups, times the index of A in its normalizer, which we can think of as being kind of like a Weil group size. Okay, so that is yeah, I mean, useful for the extreme of very regular elements. So it does a very nice job, for example, if you have an element of SLN of FQ, where the characteristic polynomial is irreducible. But it's not an exponential bound, right? I mean, it just covers one end of the spectrum. Okay, so here is now, here is something which is an almost exponential bound. So let me look at it. So G is of Lie type, and you take a semi-simple element, and now there's a technical condition that its centralizer is what they call a split levy. But this, although it's technical, this is satisfied by a lot of elements. This is not a very strenuous condition. And then what the theorem says is that the absolute value of chi of G is less than or equal to, okay, there's a constant here, so it's not quite purely exponential, but the constant only depends on the rank of G. So it's a rather mild constant. And now the rest of it looks like an exponential bound, and let's look at what it is. It's 1 minus a half times, well, a kind of logarithmic comparison of the size of the conjugacy class of G and the order of G. Now, something like this in the exponent is exactly what we want, because when the conjugacy class is small, then that means the centralizer is big. I mean, this quantity over here is close to 0, and so our bound is rather bad, which is what we expect. That's a highly singular element. And when we have a regular element, so that the conjugacy class is really huge, this thing approaches 1. And OK, we'd like the exponent ideally to go to 0. It goes to a half. So it would be nice if we could replace this a half with 1. But still, this is quite a good estimate for elements which are pretty regular. Not, of course, nearly as good as this kind of method can give, but as I say, there's no one method which does a good job on all. No known method. I mean, maybe someday on the full range of elements and characters. Okay, so this is the theorem of Bezrukovnikov, Liebeck, Shalev, Dieppe, and to kind of give an illustration of what you can do with this method, here is a consequence of this theorem, which and other things worked out by Taylor and Dieppe a couple of years later. We're limited to SLNQ when n is greater than or equal to 5. The nice thing here is that this applies to all non-central elements, and the inequality has a very simple form. Okay, it has this C prime, okay, which is going to depend on n. So it's not quite a pure exponential estimate, but this n minus 2 over n minus 1 is just about exactly what we would expect if we look at the most regular elements. I'm sorry, the most singular elements. If we look at the elements which have the smallest conjugacy classes and the largest centralizers, then we would expect to get something like this. So a weakness of this estimate is it doesn't reward you for having G which are regular, but a strength is that it covers all non-central elements simultaneously, and it's almost an exponential bound. So I like this result, and it's quite a useful result, I think, in a lot of the kinds of applications that we have in mind. Okay, so finally I want to say something about the exponential bound that I mentioned earlier in the talk as having certain applications. So yeah, I mean, this is resulted from joint work with Gorelnik and Tiepp, and it covers all groups of Lie type and all elements of G and all irreducible characters, so it covers everything. And what it's good at is another question. It's an exponential estimate, and qualitatively it looks almost exactly like the previous result, 1 minus a constant times this logarithm. The only thing which is different and worse is that instead of a half, which is not, we would have liked 1, but it's, it's not bad, all we can say about this is that C is an absolute constant. It's computable in principle, although it's extremely small. So this kind of result is great if you're trying to prove some kind of asymptotic statement about what happens in very large rank. But in any reasonable rank that you might be interested in, this estimate is in fact inferior to existing estimates like the Gluck estimate that I talked about at the beginning. So yeah, so what would be needed, I think, to turn this into a near ideal estimate would be if we could replace C with 1, or 0.99 would be almost as good maybe, but we have no idea how to do that. Okay, let me say just a few words about how to prove this result. So we use a kind of an amplification argument. In the case where G is quite regular, so the conjugacy class is big, and also chi of 1 is big, then this just follows directly from the centralizer bound. If the conjugacy class is big, but the character degree is small, and if chi of G is kind of surprisingly big compared to chi of 1, then what we can do is we can say, well, if chi of G is big, then so is chi squared of G, and so we can find some irreducible factor, chi prime of chi squared, which has higher degree than chi, but also has the property that in absolute value, chi prime of G is also surprisingly big. And so instead of considering the pair G and chi, we consider the pair G and chi prime, and in this way we reduce to a case which, some kind of Sant or induction argument, we reduce to cases that we've already treated. What happens is that the exponent gets a little worse each time we do it, and which is why we end up with a very bad exponent. So that's how we sort of amplify characters. Now, if we start off with a singular element, so the conjugacy class is small, and chi of 1 is arbitrary, it could be big or small, and again, the absolute value of chi of G is unexpectedly large, then what we can do is we take G and we take a bunch of random conjugates of G and we multiply them together. And we get something G prime. And we can show that the expectation of the absolute value of chi of G prime is surprisingly big. So for some choices, a reasonable number of choices, G prime still, we still have a large value of chi of G prime, but G prime also has a larger conjugacy class, and so we can we can reduce to the pair G prime and chi. So in this way, we kind of reduce to cases we've already seen and prove the theorem. Okay, I will stop here. Thank you very much for coming to the talk.
Thank you very much, Professor Larsen. And I also would like to thank all the audience that attended this invited lectures. I think the time is now over. So goodbye. Thank you very much.
Thank you.